Welcome students. So in the previous class we were discussing regarding the architecture of 8085 microprocessor in detail. Now let's move on to the description of how you can make use of the 8085 microprocessor to do several tasks as per our requirements. So before entering into the programming session, we will be initially looking into the machine cycles and bus timings. So what is meant by this machine cycle and bus timing, or what is its need? So basically we know that when we instruct the microprocessor to perform a task or to perform an operation, it has to perform a series of or a sequence of steps. First of all, it needs to identify the memory location from where the instruction is to be fetched. Then it has to decode the instruction which has been fetched using this instruction decoder, and at the end of the decoding session, it determines the function that has to be performed, and it proceeds to the perform perform the function that has been specified by the decoded instruction. Now if you look, all these sequence of operations, or all these operations has to be performed within a given interval of time, so that it falls into a synchronization between the control signals, and it also enables a synchronized communication between the various modules or various sections or various devices involved involved in order to complete that particular operation or that instruction. So in order to establish this synchronization between the various devices or various units as well as the control signals, we need timing informations, so that with respect to a particular amount of time which has been fixed with with reference to the clock of the microprocessor system, we will be able to, if the machine is able to achieve the task, then our instructions will be executed in a smoothful manner. So these are the major terms which is involved in defining the timing of operation of the microprocessor. We have basically three terms. One is instruction cycle, then we have the T states, then we have the machine cycle. So what does each of these mean? T states is nothing but, from the figure itself we can see, it's the period of the clock cycle. So in order to perform an instruction, the microprocessor makes use of several clocks. Okay. So one period, or the period of this clock cycle, is defined as a T state, and from the figure you can see that there are multiple T states in a machine cycle as well as in an instruction cycle. So this T state is nothing but can be defined as time that is taken by the 8085 microprocessor in order to complete a portion of the desired instruction or desired operation. Okay, and the next term, as we discussed, it's machine cycle. So machine cycle can be defined as the number of T states required, or the time that is required by the 8085 microprocessor in order to complete a specific task. Okay, so from the figure you can see that the instruction cycle consists of two machine cycles, that is M1 and M2. Okay, so M1 is a machine cycle which consists of 4 clock periods or 4 T states in order to complete a task that is included in the instruction cycle. Okay, M2 is another machine cycle which consists of 3 T states, that is which is also required to complete another portion of the instruction cycle. Okay, so if you take the machine cycle, it can be defined as the sequence of T states, or the number of T states, or the time period that is required by the microprocessor in order to complete a specific task involved in an instruction. Okay, and instruction cycle can be defined as the sequence of operations that the microprocessor has to perform. Okay, that the microprocessor has to perform in order to complete a particular instruction completely. Okay, or you can say that instruction cycle is nothing but the time required by the microprocessor in order to complete the entire operations that is mentioned by an instruction. Okay. So as we saw, T state or clock cycles per period or periods, it's equivalent to one clock period, and it is the time in which only a subdivision of the operation is being performed, and the total number of T state determines size of machine cycle required to perform an operation. Okay, so for an operation it is been defined, and we mostly define the number of T states to define the machine cycle and the number of machine cycles in order to define the instruction cycle. Machine cycle, it's a time required for completing a basic operation, and we also call this machine cycle as processor cycles. Okay, and this machine cycle uh, depends upon each of the processors, and it keeps on varying, and it also keeps on varying with respect to the clock period in some of the cases. Okay, so generally the manufacturers of the processor or the microcontroller that we make use of, the manufacturer itself defines the timing and status of various signals during the machine cycle. So if you are looking into the data sheet, we can see that to perform this basic operation, for example like instruction fetching, okay, the processor or the controller has to fetch some instruction from the memory. Okay, so for performing that fetching operation alone, this number of T states, or this is the machine cycle that has been required. So that means in the data sheet itself it will be saying that this processor requires 4 clock periods or 4 T states in order to complete this fetching operation, and during this operation the values or the status of various signals. For example, in 8085 we have seen the status in S1 and S0. We have seen that if the instruction is taken from the memory, then we will be having some deflection on the IO bar M bar signal. Okay, so what are the values of each of the signals, and what are the signals involved in each of these operations, and what will be their values? Everything will be defined by the manufacturer, and we can look into those timing diagrams or those graphical representations or the waveform representations, and we can design the system. That is, we can go for integrating the various IO devices to your processor or the microcontroller. Okay, in general for 8085 the T states that is involved in the machine cycle can vary from minimum 3 to maximum 6. Okay, so this is the range in which you won't be having machine cycle in 8085 which has 2 clock periods or 2 T states alone. Okay, so minimum number of T states which is present in the machine cycle of 8085 microprocessor is 3, and the maximum is 6. Now moving on to the instruction cycle. As I told, the instruction cycle is a sequence of operations that a processor carries out while executing the instruction, or in terms of time we can say that it is a time required by the processor to complete the execution of an instruction. Okay. Now in case of 8085, this instruction cycle can be divided into two subcycles. One is fetch cycle and the other one is execute cycle. So these two cycles will be present in most of the instructions of 8085. Okay, in some cases you can see that the entire operation, okay, the entire sequence of operation that has to be performed by the 8085 completes in the fetch cycle alone. Okay, so but or the fetching opcode fetch machine cycle alone, but in most of the cases or in all the instructions you can divide, or you can visualize the timing diagram such that it consists of fetch cycle and the execute cycle. So fetch cycle is the duration or the time that is taken by the processor to fetch the opcode from the memory, and the execute cycle is the time taken by the processor to decode the instruction and perform the work that is been specified by the instruction. Okay. So if you look into the details of the machine cycle, or now if when we move on to the analysis or exploration of the machine cycles, about machine cycles, in 8085 we basically have 7 basic machine cycles. Okay, so most all the operations or all the instructions that is been performed by, or that is being executed by the various instructions that is being accepted and executed by your 8085 processor consist of either any of these basic machine cycles or a combination of multiple basic machine cycles mentioned here. Okay, so the basic machine cycle starts from opcode fetch cycle, where we this it's a cycle or the number of clock periods required by the microprocessor in order to fetch the opcode from the memory. Okay, and memory fetch the opcode and decode it. Okay, so everything is included in that opcode fetch cycle itself. The second basic machine cycle is memory read, where this is the sequence of t states or the time required by the microprocessor in order to read a data or instruction from the memory. Okay, to read some data from the memory. Then memory write cycle in order to write some data from the register to the memory space defined in the instruction. Then IO read cycle and IO write cycle, instead of the memory you will be reading some value from the input devices in the IO read cycle, and the IO write cycle is the sequence of operations or the time required for writing some data to the output devices. Okay, and the two other basic machine cycles which are rarely used are interrupt acknowledge cycle and the bus idle cycle, which are the basic machine cycles which has to be explored when we move further into the depth of designing a microprocessor based systems. So as per our syllabus we need to explore only the first five basic machine cycles. Okay, and we can see that most of the instructions, or we have around 74 instructions in our processor. So out of this these 74 instructions, most of them consist of the combination or uh, combination of the first five basic machine cycles or one among the first five machine cycles. Okay, and you can see that this is the timing diagram, and when we go for the diagram or the waveform representation of this machine cycle. Okay, waveform representation means it's a diagram which consists of representing the waveforms of all the signals involved in performing one each of these operations. Okay, so if we go for the timing diagram of opcode fetch cycle, it consists of the clock signal, it consists of the status regarding the address and data bus, how the values has been shuffled, and what is the value for IO bar, M bar signal, S1, S0, etc., read, write, etc. All those control and status signals will be plotted in that particular waveform representation. Okay, so in this we won't be going for the ideal square wave, we will be going for the realistic square wave which has some rising and some falling edges, and all the activities or all the operations which has to be executed in a machine cycle takes place either at the middle portion of the rising edge or the positive edge, or at the falling edge or the negative edge of the falling okay, half of the falling edge or negative edge. Okay, and when we whenever we mark the t states in this machine cycle or this timing diagram, it will be either you can start from the uh, low to high tip. Okay, at this tip, or you can start at the falling edge. Okay, so the at the beginning of the falling edge. So in general, or in with respect to the 8085 microprocessor, this operations or the t state is always defined at the falling edge. Okay, it's not at the rising edge, it is always at the falling edge of your microprocessor. We always represent the components at the falling edge. So let's move on to the timing diagram. So timing diagram is nothing but a diagram which consists of a series of waveforms which provides information about various conditions of the signals. It may be your control signals, or but it can be your status signals, it can be the signals corresponding to your address or data bus, etc. Okay, while the machine cycle is being executed, so during the execution of that particular task which is been is been mentioned in a specified machine cycle, what are the status of each of the signals. Okay, So let's look to the first basic machine cycle of your 8085 microprocessor, that is opcode fetch machine cycle. So from this figure you can see that this opcode fetch machine cycle consists of 4 T states. Okay, so that is a basic. So if you go back you can see that you have the opcode fetch cycle starting from 4 T states to a maximum of 6 T states, where this 6 T state opcode fetch cycle is mostly or is basically used when we go for some bus idle operations or some interrupt acknowledgement operations. Okay, if there is an opcode fetch operation due to an interrupt, then we need to go for the six T states. Okay, so for the time being, as per the syllabus, we need not go for this six T state opcode fetch cycle. We will be just concentrating on the uh, 4 T state opcode fetch cycle. And you can see that for all other operations, we need only 3 T states. So it's basically a symbol. So if you are aware about these 5 basic machine cycles 4 and 3, you can have the instructions timing. You can also draw the timing diagram of various instructions that is supported by 8085 microprocessor as a combination of opcode fetch or machine read, opcode fetch or machine write, memory write, opcode fetch and IO read, or opcode fetch and IO write. Or itself in most of the cases out of the 74 instructions you'll be seeing in the later classes, where there are a lot of instructions which can be completed, or the instruction cycle itself can be completed by the single basic machine cycle, that is the opcode fetch cycle itself. Okay, so this knowledge, or the thorough knowledge about the machine cycle representation of these 5 basic operations is enough for developing the timing diagram of the various instructions that is supported by 8085 microprocessor. Okay, so it is a 4 T state machine cycle, and at the falling edge, okay, you can see that first uh, in the first falling edge of the time T state, the address is being placed onto the address buses. That is, the higher 8 bit information of the address is been placed on the A8 to A15 bus, and the lower address byte is been placed on the AD0 to AD7 bus. Okay, at the same instant itself, the address latch enabled signal is going to high. The read signal is in the high state by default, because we whenever we need to enable the read signal, we need to place a low value. Okay, now we are not enabling, so we are placing it at RD bar as high itself. And since this opcode fetch operation is an operation that has to be performed by reading the instructions from the memory, you will be placing the IO bar M bar signal equal to 0. Okay, you will be placing the IO bar M bar signal as low, and as we have seen in the early classes, corresponding to this operation, the status is indicated by S0 and S1. Status signals S0 and S1 is equal to 1. Both are equal to 1. So you can see that both of the signals are having the 1 value. Okay, so at this instant, so why we draw this cross mark here is just to show that you are having some sequence of 0 to 1. Okay, so what is the actual value now? Previously this AD0 and AD0 to AD7 and A8 to A15 was having some sequence of zeros and ones, that is some address values. Now at this instant it is shifting to the new value. Okay, so in order to show that the current sequence of zeros and ones placed on the address lines, okay, placed as the address information on AD to A8 to A15 and AD0 to AD7 lines are different from the previous. In order just to indicate that difference, we are showing here a crossbar here. Okay, and ALE, the address latch enable should be always high at this stage, because if it is low it will be enabling the latch, so it is not the time for enabling latch, so we will be placing it in the opposite action as we done for the RD bar. And this is to indicate sometimes in the previous instruction it may be again the S0 and S1 is in the 1 is equal to 1 itself. That means the previous instruction, okay, if you draw the machine cycle for a continuous 3 instructions that is been executed, you may be seeing that this S0 and S1 is equal to 1 in the previous state itself. Okay, but to indicate that at this particular instant alone, okay, if you are taking this instant alone, previously there was some operation which is different from the opcode fetch. Okay, so now transferring to the opcode fetch operation, we need to change these values. Only for indicating that, we are always drawing the status values or the corresponding values for this particular operation uh, in the opposite manner. Okay, so from, if I need 1 and 1, I will be drawing from 0 to 1. Okay, and if I need 0, I will be drawing from 1 to 0. So at the first falling edge of the clock cycle, you will be placing the lower address bytes on the AD0 to AD7 bit buses lines, and higher address bits on the A8 to A15, as well as you will be placing the ALE to the higher level and RD in the lower level, and IO bar M bar is low, and S0 and S1 equal to 1. Okay, now at the middle of the first clock cycle, that is apart from this, okay, at the middle of the first clock cycle, that is at the middle of the rising edge of the first half cycle, you will be placing ALE as low. Okay, so at this point, when you make this ALE as low, what happens is that it is the time, or this transition of the ALE signal from high to low state indicates the enabling of the address latch, and the lower byte address which was available on the AD0 to AD7 lines will be latched to the address latch. Okay, so after enabling this, it takes some more time for latching the address information from AD0 to AD7. So we will be extending this availability of the low byte address on the AD0 to AD7 bus up to the end of the first clock cycle. Okay, now you can see that at the beginning of the second clock cycle, this has been completed. The address information which was available on the AD0 to AD7 lines has been latched to the address latch, and now there is no value on the bus. Okay, now there is no value on the AD0 to AD7 bus. So you can see here the value or the condition or the status of the bus has gone to high impedance value. So this dot always indicates it is a high impedance value. High impedance value means it is not logic 0 or it is not logic 1. Okay, so at the beginning of the second clock cycle, all the values, so here you can see that the address has been stored to the latch, and now your AD0 to AD7 is free to read the opcode from the memory. So it is the high impedance state. A8 to A15 now also has the high byte address, and address latch enable is low right now, which shows that now the AD0 to AD7 bus is all required for transferring the data from the memory or the IO device. Okay, now since it is a opcode fetch operation, it is always from the memory device. Okay, and now at the beginning of the second clock cycle, you will be making RD bar as low, which says that now the processor can read the opcode from the memory. Okay, so making this RD bar as low enables or indicates the CPU to read the opcode from the memory, and it goes to that particular memory location and starts reading the opcode memory. So, and now you can see that up to the end of the third clock cycle, the RD bar will be low, and during this time you will be the opcode which is available in the memory is now available on the AD0 to AD7, and the microprocessor CPU can read this opcode which is available on the data bus. Okay, which is available on the data bus, and it can read it, and it can pass it to the instruction decoder, and it can perform the decoding operations. Okay, so for the instant of time where RD bar is low, you can see that opcode is there. As soon as the RD bar goes to high, then the opcode information which was available on the database is being vanished. Okay, so this indicates that for the time duration where RD bar is equal to low, you can read something from the memory. Yes, and this is applicable for write whenever WR bar is low, the data can be that the data will be available on the database, and it can be returned to some of the memory or the IO devices. You will be seeing that in the future. There is no change for the S1, S0 or IO bar, M bar signal. It is always the same, because this are the status signals which is indicating the operation that has been performed. Now it is always operation with respect to memory, as well as the operation is fetching of opcode. So S1 and S0 equal to 1. So at the end of the third clock cycle, you will be placing the RD bar as high, and at that instant the opcode that was available on the database has been vanished, as well as at by that end of the third cycle, the address byte which was available on the higher address byte which was available in the A8 to A15 has also been vanished. Okay, and now you can see there is one additional clock cycle, that is T4. So during this T4 or the fourth clock period, what happens is that you can see the values of ALE, RD bar and IO bar, M bar, S1 and S0, everything remains same. Only deflection, or what is a change here, you can see both the address and data bus has gone to the high impedance state. So this duration, the last one clock cycle in this opcode fetch machine cycle, is the time taken by the microprocessor in order to complete the internal operations that has to be done after fetching this opcode fetching. Okay, so in the first three T states, the processor will be fetching the opcode from the memory, and the remaining one T state is used by the processor to perform the internal operations by to perform the internal operations. So in some cases, soon after fetching the opcode from the memory, it identifies that it has to add two values which is available in the two registers, for example A and B. Then the microprocessor will be making use of this one T state to add those two values which is available in the register. Okay, that's an example which I told. So that is what is meant by the internal operations. Okay, it can be even some logical operations also. Okay, so that's about the opcode fetch machine cycle, and these are the slides which explains what I have already explained to you right now. Okay, thank you all.